Hello and welcome back to Calculus 3. This is section 14.3 on conservative vector fields. Before we go into conservative vector fields, for purposes of future theorems, definitions, and so on, we need to talk about types of lines and types of regions that we have. They do have a very lengthy definitions, I mean lots of words. So by drawing simple 8 pictures, we can quickly define what these curves and regions are, give them names, and then be done with that. So I'm going to divide this space here into 8 regions. And then I'm going to put in each one of these. So these are not XY coordinate systems. These are just space divided. All right. So now we have a potato-looking one right here. This is a curve C, and this one is closed and simple. Closed and simple. And then we have curve C like this, which is not closed, but it's still simple. Now, clearly, closed and not closed are what is the difference between the two. They're both simple. Now, you might ask, well, what does a simple means? Well, here is a closed not simple. So it intersects itself, and then over here we can go with like that. And that will be not closed and not simple. So we are looking at if it intersects itself, it's not simple, and then you have open and closed, which is closed and not closed. So that would be for a curve C. Projector will eventually stop shaking when it reaches its normal operating temperature and fans stop annoying it. Then we have regions. So we draw a potato-like one, and we shade inside. We will call this region R. And this one will be connected and simply connected. Then we're going to have a potato region with a hole inside. We are going to have 2 regions, and then we're going to have 2 regions where one or both will have a hole. So I'm going to now do the shade. No coughing. Thank you. And we have region R, region R, region R, right? So all of these are region R's. And now we have the second one is connected, but not simply connected. So connected, not simply connected. And then we have not connected, but simply connected. And both knots now. Not connected. Right, you have 2 separate regions, and then not simply connected because there is a hole inside.
So
The textbook will provide you with those lengthy, as you can see, definitions in those two boxes, and those boxes explain both of these charts, tables of possible situations that you may have. So now we are going to go into conservative vector field, define conservative vector field, take a look at the test for conservative vector field, and then after that figure out how to find the, how to find the potential function which generates conservative vector fields. So we start with definition for conservative vector field. That's the VF. A vector field F, vector field capital F with the thing, there we go, is said to be conservative on a region R2 or R3, depending on where you are, if there exists a scalar function phi such that vector field is the gradient of phi on that region. This is something that I mentioned earlier when we talked about, I think last week, last week. We talked about vector fields, and I said vector field is a function, blah, blah, blah. It's functions inside the vector, and you know that you can get that if you have the derivatives, right? So there it is now. So a vector field F is said to be conservative on a region in R2 or R3 if there exists a scalar function phi such that F vector field is equal to the gradient of that phi. So now we need to take a look at the test for conservative vector fields. So what is the test? Let vector field F be FGH, right, as we are all used to. Now, we don't actually put f of xy, fy, xyz, because this could be for 2D or 3D, so we'll just leave it FGH. So be a vector field defined on a connected and simply connected region region D of R3, where F, G, and H have continuous first partial derivatives on D. Then F is conservative if and only if, and now we have conditions. So partial f partial y is equal to partial g partial x. Partial f partial z is partial h partial x. Partial g partial z is equal to partial h partial y. So these are all combinations that we can get. All three together are R3. So we have all of this is for R3. If you only have the first one, that's for R2. So you can have R2 or R3 problem. These are your tests, right? These are separated by commas, right? These are three separate equations. And it's very simple to remember this because look, f and g and then y and x. So, right? F and h and that's a z and then it's x. And then g and h and then y and then z, right? So all combinations of these, you can construct this quickly. And obviously if you only have f and g, then you only have x and a y. Just make sure they are switched. So this is the test, and you have to check this. Those of you who took differential equations, remember this test from exact equations in chapter 1. So this is the same stuff. So now what do we have? We have, let's say, a vector field given as, so let's go and check one of these fields, and then we're going to do the rest. So how about, let's do (14) looks terrible enough. So problem 14 says test, and then we have vector field is given as vector 2x cubed plus xy squared, no coughing, comma 2y cubed plus x squared y. So this is R2. So the only one we are using is partial f partial y needs to be the same as partial g partial x. So we know that in the vector field, the first one is f, the second one is g, and then we just check. So we have partial in respect to y. Well, that's going to be 2xy. And that needs to be equal to partial in respect to x. The first term dies, it's 2xy. Nice. Yes. It is conservative. So it's a conservative vector field because the condition checked out. So now, since this is a conservative vector field, that means that we can find a scalar function phi, which would generate this field if you are to take the del of it, right? If you apply the gradient. So what do? Well, to find the potential function, we have to learn the procedure. So now, procedure to get phi xy. Now this is in R2 because our input is in R2. We are also going to do R3. So what do we know? We know that our vector field f is equal to del of this function phi, right? So what we actually have is the vector of partial derivatives of phi. That's what we have. So our vector field is the vector of partial derivatives. So vector field is given as f comma g, and these puppies over here are partial derivative in respect to x and partial derivative in respect to y. So it's very quick to see that your partial derivative of what you are looking for, therefore, hello differential equations, your partial derivative in respect to x is equal to f. And f in this problem is given as 2x cubed plus xy squared. So this over here is partial differential equation. Because you have unknown function phi, and you have a partial derivative in respect to x of that unknown function phi. The answer for any differential equation, if you never took Calc 2, is a function. So in Calculus 2, we have a section where we teach that you guys had, a history of solving equations, and every time the answer was a number. Whether that equation was exponential, logarithmic, quadratic, doesn't matter. Whatever equation you had up to that point, answer was a number. Differential equations have functions as answers. So now you are looking at what we call a partial differential equation. Now, this partial differential equation is partial of phi, partial of x, is equal to 2x cubed plus xy squared. To undo this, we, dare I say clearly, need to integrate both sides in respect to x, which will, right, you put integral dx like this on both sides, and if you take a look what happens on the left, integral knocks off the partial over there, and then dx cancels dx, so you are left with phi of xy, which is what you're looking for, right? That's the answer already. And on the right-hand side, you just need to integrate, but you know how to integrate, and you're integrating in respect to x, so all of your y's are constants, and you just plow through this. So you have x to the fourth over 2 plus x squared y squared over 2. So when you integrate, that's what you get. And now, here is the $1 million step, plus c as a function of y. Now, that is important. This c here is a function of y because you are supposed to add a constant in x for x integration. Well, if there was some kind of, let's say, y squared over there, if you are to take partial derivative in respect to x, it would die, right? So any function there, e to the y squared, e to the sine of y squared, whatever you can conceptualize as a function in terms of y, could be a constant term, because x would kill it. So you can't put plus c, you have to put plus c of y. Now, believe it or not, this is already an answer, but we are not happy with it because we have c of y. So we have to go on. So this is already partial answer. We go on to compute c of y. So how do you compute c of y? Well, guys, this is already your answer. This is your function phi. Now remember that you haven't used the partial derivative in respect to y yet. So you are going to find the partial derivative in respect to y. And in that case, the first term dies. The second term is going to be 2x squared. No, it's just going to be x squared y plus the derivative in respect to y, because now you are taking the derivative in respect to y. You have the unknown function in respect to y, so the derivative of that better be c prime. and you set this equal to your g, which is 5y. So that's 2y cubed plus x squared y. So this step over here is generally the one that causes all the hysteria and confusion. Set equal to g. What is g? G is partial derivative of phi in respect to y. If you go back, you see that g is this. So I have g given in a problem, and I have another g that I can compute from my calculation from here. So I have two g's, and I just make them equal. So now, as you can see, this term drops, and from here you know that your c prime of y is equal to 2y cubed. Now this is differential equation that you need to solve. This is dc dy is equal to 2y cubed. You can separate the variables, and so dc is equal to 2y cubed dy, and then integrate both sides. So I'm just going to write over here separable differential equation. Those of you that are having a panic attack right now, I'll just say 7.9 in the text. Is it 7.9 or 7.8? 7.9, right? It's one of those sections. I was right, 7.9. 7.9 separable differential equations. What do we talk about? So now we integrate, we get c, which is a function of y, is going to be equal to y to the fourth over 4 plus some constant k. You can't use c because we used c already. So now it's k. Over 2, that's what I said. Please pay attention. It's clearly over 2. Look, over 2. That's number 2. Number 4 looks like this. It's a completely different thing. All right, so now, I know. There we go. So now plug this in. Plug in phi xy, and we're done. So the answer is phi of xy is equal to, go back where we circled it, x to the 4 over 2 plus x squared y squared over 2 plus, and now it says c of y. We just calculated c of y. It's y to the 4 over 2 plus k. This is the full answer. So that's the answer. There's your potential function. Now, check. Del of phi is going to be a vector of first partial derivatives. Partial derivative in respect to x is going to be 4x cubed over 2, so 2x cubed, plus 2x, 2 and 2 cancel, x, y squared. The derivatives of these two guys are going to be 0 because they have no x in it. So that's the first one, comma, and now in respect to y. Well, no y here, so that dies, and this dies. There are no y's there. And I have the derivative of y, so that's going to be x squared y plus 2y cubed. And if you look, this was exactly the vector field that was given to us to begin with. So the steps are: figure out if the vector field is conservative. If the vector field is conservative, you can unleash this procedure to figure out the potential function which generated that field. And hello jobs, okay? Meaning your work. Vector fields are things that you measure. You take the probes, you throw them into tornado. They spin in a tornado and they send you data. What do you have? You have data on the vector field. You have a magnetic field, you have electric field, you have gravitational field. You can measure those fields. Once you have data for the fields, you have equation for that field. It's a function. And then, if that field is conservative, you come up with an equation, which is a scalar equation, potential function, which generates that field, and you can create devices that make that field. That's what the jobs are when you start working, all right? So now clearly you have the cutting edge research and you have stuff that it's already well established. So we know very well the way the electrical motor works with a magnetic field inside. So now the question is, you know, is the motor that was developed 100 years ago as good as the motor that is in the Tesla car? Obviously not, right? A lot of development. Is it the same principle that drives both motors? The answer is yes, all right? So now it becomes like, how can you manipulate the field, how you can make it better, and so on. Electric and magnetic field are the fields that make your liquid crystal displays work, the LCDs. We are talking about your screens on your computers, the screens on your TVs, the screens on your smartwatches and calculators. Those are all liquid crystals. Liquid crystals are very small rods that orient themselves when they find themselves in a magnetic field. So the way to manipulate of what is on the screen is simple manipulation, local manipulation of magnetic field, so that the rods orient themselves and let the light behind that rod pass through and hit your eye, or get blocked by the rod because the magnetic field flipped. Now, LCD technology is really old, right? You can go to Microsoft Store and you can try on the Hololens. The world of holograms is already here. You can actually look around and put another layer of augmented reality on top of reality. Google Glass was the first attempt at, and if anyone wants to try out the Google Glass, I have one. So in my office. So if you want to see, and Google Glass is really cool. You put it on, right? It has a little display above your right eye, and it can display your text messages, your email, you can ask questions on the Google, it will answer because it does have a speaker as well. It does speech recognition, it can take videos, photos, and it also has a GPS in it. So as you are driving, right, that thing is right there. So it tells you left, it tells you right, and it just shows the arrows and the road, which way it curves. It is a really cool thing. So now with the HoloLens, that is a completely new level of what you guys see. Now Intel is producing something that are glasses that are a little bit thicker frame than this. Again, full computer inside. With a micro laser, they are projecting the image at the retina of your eye directly. So think about that one then, right? all of these things, right, are in development. LCD and little crystals, and this being an ancient technology in comparison to what's in the research and what it already exists today. So there's a lot of things, guys, that you will have to upgrade on top of this concept to work on those fields now, which is why for the 50,000th time in this class, I am asking you to join clubs and projects and things at your whatever school you're from to actually have some or any skills upon graduation. No one cares about your grades anymore. I'm sorry. Well, they're completely pointless and useless because the level on what you get grades is completely insignificant anymore. This stuff is 250-year-old calculation that we already have on the market, worked out, and you know, whatever. We are thinking now on what is the next thing. Like liquid crystal display is something that we mastered a long time ago. Now, let's see if we can actually have some way of telepathically controlling our cell phone. Yes. With a field that we are creating in our brain, which might be conservative, which might, you know, and so on and so on. And now you're looking at me and saying, oh, look at this guy likes science fiction. Exactly. Every single device you touch was a science fiction or a crazy idea or an impossible idea or a witchcraft at one point in history. So now, go on, have the craziest idea possible, and then work on it, because that's what doesn't exist, right? No one cares when you write on your resume, able to work in Microsoft Office suite. I read a resume 2 weeks ago with that sentence, and I'm thinking, yeah, my 5-year-old is too. It's not a skill anymore. It's just you are born with it. It's in your genes because you just exist. You are able to type on the computer. That's given. Yeah. I said don't worry about it. We can build an ark. We need to. There are the trees over there. Yeah, I know. See, you might want to unpack now, Jacob, because...
I was just about to leave it.
It's because of you. This is like the second strike you have today. Like, first one was having a test, and the second one is this.
Yeah,
like, you look at the horizon, it's not cloudy, right? It's nice. It's just raining here. Like, how terrible of a person you have to be for the rain to follow you, just like where you are. That's where it rains, like right there. Anyway, how about we do one of the 3D things? Let's go, guys. Do this. Do this a little bit. There we go. Now we do this. We're going to do a 3D problem now. R3. There we go. Now, when you have everything worked out, we are going to take a look at the oh, this is your window to run. We start at problem 20, where the vector field is given to us as yx1. We have to check if it's conservative, and if it's conservative, go ahead and find the potential function. So, is it conservative? Well, we need to have partial f, partial y to be the same as partial g, partial x. Okay, let's check that. So, partial f, partial y is 1, and partial g, partial x, 1 equals 1. Nice. Yeah, it passed the first out of 3. Let's go. Partial f, partial z needs to be partial h, partial x. Partial f, partial z, partial f, partial z is 0, right? And partial h, partial x is 0. Well, he passed that one. Partial g, partial z, partial h, partial y. So partial g, partial z is 0. And then partial h, partial y, 0. Great. Check, 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 big fat check. He checked on all three conditions, so we can go ahead and look for potential function because this worked out. We are looking for function phi of x, y, and z such that del phi is going to be equal to our f. Del phi is partial x, partial y, partial z is equal to our f, g, h. Great. So partial x, you can start with any one you want. Well, let's start with x. So partial x is equal to y. This is a partial differential equation. We have partial phi over partial x is equal to y. We are going to integrate in respect to dx both sides. Same steps. And we have phi of x, y, and z is equal to xy plus some constant function c in y and z. We integrated in respect to x. Therefore, y and z are both constants, and that's why we have a constant function of y and z. Now, this is already a partial answer. Okay? Partial answer. We go on to calculate what we don't know. The next step is to take the partial derivative in respect to y. We are going to get x plus partial c and partial y. And this is still the same function, right? And now we set that equal to whatever the partial y was in a g spot, that's x. So when you set these two puppies equal, you get that your partial c, partial y is equal to 0. Set it equal to g. Alright, so now what do? I integrate both sides in respect to y, and I get that c of yz is equal to 0 plus a constant, but as a function of z. So now that plugs in up there. Plug in. And now we are closer to our answer because we have that our phi xyz is equal to xy plus now k of z. Now this is again partial answer, but it's better. So let's call it better partial answer. I think this is where the idea of partial credit on exams started. It's way too many steps, and the student, hey, can I have a partial credit for partial answer? And whatever professor said yes, and that it became a standard. I think that's where it started. So the last step is to take partial of z, which is 0 plus, this is just k prime of z. So you have partial phi partial z is equal to k prime of z. And now we are going to, well, let's write this as dk dz. And now we are going to integrate both sides in respect to z. So over here you get that the oh wait, hold on, wrong, bad, terrible, terrible. We need to set this equal to, you have to set this equal to 1. You have to set it equal to 1 because that's what your age is. Where's my orange? Set it equal to age. There we go, much better. So now we have dk dz is equal to 1. That's a separable partial differential equation. So dk is equal to 2dz. We integrate both sides, and from there we get that the k of z is equal to z plus some constant m. Where? This spells kzm. It's like a magic word. Kzm. So now you plug that up there. That was green. Plug in. To get your final state of the function, it was xy plus z plus some constant m. And that is the answer. This is called potential function. So now, as any good student who cares, you will check, because it's easy. All we need to do is to find del of phi. Partial derivative of the whole thing in respect to x is y. Partial derivative of the whole thing in respect to y is x. Partial derivative of everything in respect to z is 1. And there you go. We started with the vector field yx1, and we now have the scalar function which generates that field. So it's a lot of chasing around, right? But once you figure out the pattern, you will just say, joke. And the pattern goes this way. You know the formula, because, and then you know that the del of phi is 3 partial derivatives. You know that your vector field gives you 3 functions. So each one of these is equal to its corresponding FGH. So you start by equaling any two. Generally, we always start with x equals f, but you can start anywhere. You can start with z equals h if you want to. And you go through one each by one. So what I do is I say that phi of x is equal to f, which was y. Then we integrate whatever the variable you started with. If you start with f of x, you integrate with respect to x, and you already got your answer. And then from there, you start differentiating with the next one. So we got the answer using x, then we differentiate that x with respect to y, and we set it to the next one, which in our case was x. And then go through these one by one And at the end, we have the answer. Yes? Alex?
Can you just go to the part where you said it equals G?
Part where I said, yeah, right here. So I got my first partial answer by using the partial derivative of x. So now this is the answer to the problem. We don't know this piece, but this is already the answer. If you take the partial derivative in respect to x and the partial derivative in respect to y, you're going to get your y and x, the first two. You don't have the z one worked out yet because you haven't solved this. But most of the answer is already done. Now you want to do a better job. So to do a better job, you take your answer and you do the partial derivative in respect to y. You get this, and then you set that equal to g, which was the partial derivative in respect to y. And then x and x cancel, giving you that this is equal to 0. Then you solve that, right? Again, separation of variables, integrate both sides, whatever it works, to get what c is equal to. So now you have that this function c is equal to this. So you plug that in there to get the function below. So we reduced our c of yz into a function k of z only. And then we do it one more time now, partial derivative in respect to z this time, and that calculates kz, and we are done. This can be done in any order. Now, as a student, I was interested in these kind of things, and I would take one problem to master this. I would take one problem, and I would solve it all three ways. I would do there are 6 ways in which you solve it, but I solved it in x, y, z order, y, z, x order, and z, y, x order, you know, and they all give you the same at the end. It doesn't matter which order you solve it in. Why are we looking for potential functions? Well, as I said earlier, if you know which function generates the field, you understand the field very well. You can measure the field, you can come up with the equation, you can make stuff with it, right? Now, from math standpoint, didn't we say we want to evaluate line integrals? Yeah, we said we want to evaluate line integrals, right? So now there is something is called fundamental theorem of line integrals. And it's going to create an easy way for us to calculate line integrals that fit certain category. Now, this is a procedure, but it's a very simple procedure. Maybe you want to do this instead of doing the line integral stuff with the vector field. Maybe you don't want to do this. Maybe you do want to do the line integral stuff with the vector field. So, whatever. But let's define these things and then see. So, fundamental theorem of line integrals. So fundamental theorem of line integral says that our let f be continuous vector field on an open connected region R2 or R3. So let f be a continuous vector field on an open connected region in R2 or R3. We can find potential function for both of them, right? There exists a potential function phi with the good old specs that vector field is equal to del phi, right? if and only if line integral f dot t ds, this is the standard one we've seen 15 times so far, which also can be written as f dr, right, is actually f of b, phi of b minus phi of a. You don't get to do any calculus. You get to do arithmetic instead. Because, guys, for all a and b in R2 or R3, depending which space you're in, and all piecewise and all piecewise smooth oriented curves C in R2 or R3 from A to B. Remember how you had a line segment that goes from 0, 0 to 5, 5, and then you had the vector field? If that vector field is conservative, you get to plug in 0, 0 and 5, 5 into potential function and compute line integral like this. Yes?
What does it say after smooth?
After smooth, oriented curves, there is a D at the end which is silent. Oriented curves C in R2 or R3 from A to B. This is cool. Anyone? You're like, yeah, whatever. Shall we test this? Of course we should test this. This is a ton of fun. Look at the alternative. Go outside. Why? You paid thousands of dollars to be inside. Hint, never go outside unless you have to. All of the dangers are there. All of it, right? Stay inside. So let's go and test this. What was my previous problem? The vector field was y, x1. And let's make it to be on line segment 1, 1, 1. Oops. To 5, 5, 1. Actually, you know what I could do? Instead of fixing a problem, let's do a full problem from scratch. That way we practice everything. So let's go and evaluate a line integral using this, but then for okay, so let's do one of these problems at 27 to 30, because if it's better if we do the full problem than if I'm patching the problem. Then so let's do, for instance, 28. It's nice because it has the polar stuff in it, and so they give you a potential. This is lame. So a potential function is given to you, it is x squared over 2 plus y squared over 2. And your C is the unit circle with t from 0 to pi. So it's not the unit circle, it's half of the unit circle. You have to draw this, guys. That's what it is. It starts here at 1, 0. It goes oriented this way, and it ends here at negative 1, 0. This is your A, this is your B. So now, what are we supposed to do? Evaluate the line integral. Great, evaluate the line integral. It's phi of B minus phi of A. It's like f of B minus f of A. For fundamental theorem of calculus, this is fundamental theorem of calculus for line integrals. So, phi of B, so what is the phi of B? Phi of B is going to be negative 1, 0. So this is negative 1 squared divided by 2 plus 0 squared divided by 2. So that's phi of B minus phi of A, which is 1 over 2 squared plus 0 over 2 squared. You get 1/2 minus 1/2, and you get 0. It's not 1. Yeah, no, it's not 1.
No, it is.
It is 1/2. I just put the parentheses wrong on the other one. Yeah. Come on, eraser. There we go. All right. So it's 1/2 minus 1/2. Now, if I do this the long way, which is going to practice the previous lecture, we find the vector field as del phi, and that is going to be x and the y, right? That's what we have. So partial derivative in respect to x is 2x over 2, which is x. Partial derivative in respect to y is 2y divided by 2. Yeah, that's it. So now we just need to crank the rest. We have our parametrization C, which is R is cosine t sine t in a vector. And then we have the R prime as negative sine t cosine t. And we have t is between 0 and pi. So now we have our integral 0 to pi, no coughing, and then we have cosine, so x, so this is our f, this is our g. So f dy cosine squared x minus and minus gives us plus. Oh wait, hold on, no. It is minus sine t cosine t plus sine t cosine t dt, which is equal to integral 0 to pi of 0 dt, which is big fat 0. There we go. Cool. All right, good. So 0 equals 0. If you have potential function, these calculations get to be much quicker. So this is in some sense quality of life, right? Whether you want to do the partial derivative stuff to find the potential function when you have the or you want to. Now this is also the link from your scalar functions to your vector field functions, and then why the line integrals work for both of those. We had everything of that in 14.2 together, right? First half and the second half. Ta-da! I know, right? Tomorrow, Green's theorem. See you.